I'm Kaime Fu. I'm a professor in the physics department here and a member of the Frontier in Physics Lecture Series Committee, and it is a great privilege to welcome you to David Charbonneau's talk within our series. The goal of the Frontiers in Physics Lecture Series is to bring to the University of Washington and to Seattle public lectures on the most exciting developments in physics given by the scientists who are at the forefront of making these discoveries. This semi-annual lecture series seeks to be as broad as the field we're trying to represent. We are representing. The past 5 lectures has led us through the detection of gravitational waves, the development of clocks based on single atoms, which are able to detect the change in the rate of time due to an elevation of 1 foot. And it has allowed us to follow a thread that could link a mass extinction on Earth to dark matter in our universe. If you are new to these series and any of these sound intriguing, they are all online right now, videotaped, so you're welcome to go and take a look at these past presentations. And tonight, we'll learn about recent discoveries that may help us determine how probable it is that life other than ours exists in our galaxy. This series would not be possible without the tireless work of the Frontiers of Physics Lecture Series Committee and the generosity of private support. So I want to take a moment to thank the committee. If you could please stand. And also the benefactors, Dr. Patrick O'Hara and Dr. Katerina Randolph, whose vision it is the reason why we're sitting in this lecture hall today. Okay. If you enjoy this series and are looking for ways to further your own engagement with physics, further the public's engagement in physics, or even further physics itself, the frontiers of physics, feel free to contact me after the lecture, come up and talk to me, contact our department. Just send me an email, send the department chair@physics, uw.physics.edu. Blaine will thank me for that. No, really, you should reach out to us. It can be as simple as inviting your daughter to the lecture tonight or inviting your neighbors to share the joy that we have in physics. It could be supporting and inspiring young women to go to the undergraduate, the conference for undergraduate women in physics, which actually we are proud to host at University of Washington this year, and we just got 284 applications from the Pacific Northwest. And it could also be as large as supporting a young aspiring, supporting a fellowship for a graduate student. So some of you may know that David Charbonneau was the first person to observe the transit of an exoplanet in front of a star. What you may not know was that he did this as a graduate student in a parking lot in Colorado with a 4-inch telescope, right? So, it is not a very well-kept secret that the people who are on the ground doing the work, making the discoveries, are our graduate students, and we're very proud of them at University of Washington and beyond. Okay. So, moving on to introducing David. Professor Charbonneau is currently a professor of astronomy at Harvard University and the principal investigator for the MEarth Project to detect habitable planets and for the NASA Spitzer and Hubble Space Telescope studies of exoplanets. From that very first transiting exoplanet observation, he's been at the forefront of exoplanet research, including the first measurement of an exoplanet atmosphere, the first detection of light from an exoplanet, and the first discovery of an Earth-sized exoplanet. Please join me in welcoming Dr. Charbonneau to the University of Washington.
Okay. Are you ready? All right. If you take a camera and you open up the shutter and you point it at the night sky, all right, this is what you get, okay? It's stars all the way down. And it's not a surprise to you that our galaxy contains 300 billion stars. And our galaxy is perhaps only one of 300 billion galaxies in the observable universe. So it seems to me it's a very natural question to wonder whether or not we are alone. We are not the first generation to ask that question. In fact, if you look back in the written record throughout human history, you can see that humans have wondered about whether or not, well, this is it, okay? Here we see in writing from Epicurus, more than 2,000 years ago. And Epicurus wrote in a letter, there is an infinite number of worlds, some like this world and others unlike it. Some of these worlds contain the seeds out of which animals and plants arise, and all the rest of the things we see. So long before we understood that the points of light in the night sky were stars, and then there might be planets around those stars, we still had this yearning to know whether there were somehow other populated worlds that we could come into contact with. If we zoom ahead and look back only 450 years or so, we see now much more concrete thinking about where that life might be. Okay, and so here is some writing by Giordano Bruno. He was a friar, and he said there are countless suns and countless Earths all rotating around their suns in exactly the same way as the planets of our system. The countless worlds are no worse and no less inhabited than our Earth. Okay? So what is so special, why I'm so excited, is that although humans have wondered about this for thousands of years, we are the special generation that for the first time in human history is going to have the technological ability, if we choose, to go and answer this great question. So why has progress been so slow? Why didn't Giordano get to make these discoveries? So let's think a little bit about how we want to go and find out about whether or not there's life on other planets. So we're going to consider different ways of approaching this problem. Okay, so here's one idea. What's that? Spaceship, okay? Let's build spaceships, right? Let's build spaceships, let's go to other planets, and let's see whether they've got life on them. That would be great, wouldn't that be great? So I love spaceships, I love Star Trek. This is not the way we're going to make these first discoveries, okay? If you take the fastest spacecraft that we've ever built and you pointed it directly at the closest star, it would still take more than 50,000 years, 50,000 years for that spacecraft to get there. We simply do not know how to accelerate things to a high enough velocity to get to the other stars, okay? There are people thinking about spaceships, and it's very exciting, but that's not how we're going to make these first discoveries. So let's think about another idea, right? Yeah, right? Fantastic movie. Like, I cried. Like, I still cry. I watch it with my 4 daughters, and I really cry, if you know the plot of this story, okay? And so, maybe we should be listening for aliens. And again, I mean, there are people working on this, and I'm really excited that they're working on this, but I don't believe, and I think what I'm going to tell you about today, I don't believe this is the way to make those first discoveries. And the reason is, in this case, I think when you start requiring that life not just be alive, but that it be intelligent, that it wants to communicate, that it's interested in radio telescopes, that is a very narrow search for life. That's really looking for other humans. And there may be other humans out there, but I'm going to advocate that we need to create and cast the broadest net possible when we go and actually make the first search for life outside the solar system. So what's the challenge? Okay, here's the challenge. So here's the Earth. This is the kind of thing we want to find. This planet is great. Everything you have experienced, all the great writing and human thought and poetry and complicated politics we're all experiencing at the moment, it all belongs here on this planet. And the first thing we got to know is this planet is really small. Okay, so let me compare this planet to another planet in our solar system, right? That's Jupiter. So drawn to scale, that's how big the Earth is compared to Jupiter. Okay, so the Earth is really, really small compared to even other planets in our own system. And of course, the trick when we're looking at other stars is that the light from the star overwhelms the planets. So let's now put these two planets drawn to scale next to the sun, okay? So that's the correct size of the Earth compared to the sun. And you can immediately see what the challenge is and why poor Giordano had no chance of actually finding Earth-like planets around other sun-like stars. So what's the trick? What allowed us to suddenly make progress? And actually, I showed it to you at the very beginning. Did you catch it? It's not a period. It's not a period, okay? That's an actual image. It's not photoshopped. That's a true image of the sun at a very special moment a few years ago, June 2012. Anybody? What happened? Venus. Venus went in front of the sun. If you didn't see it, not a problem. The next one is 103 years from now. So, sorry. But so this idea that that planets occasionally go in front of their stars, that's the hook. That's the way we're going to get at this question. And in particular, something very exciting happens when planets pass in front of their stars. Okay? If we zoom in on Venus, okay, this is Venus now, okay? So the sun drawn to now would go way, several stories below us. I'm just zoomed in on Venus, and this is when Venus is just creeping onto the limb of the sun, okay? In 1761, okay, a Russian scientist by the name of Lomonosov first observed that even before Venus was entirely within the confines of the sun, the outer limb of Venus was bright. And he said, that must be refraction. And what we're seeing is light being bent by an atmosphere, and therefore Venus has an atmosphere like the Earth has an atmosphere. And it was a remarkable inference, and he was right. He was right. This is proof hundreds of years ago that Venus had an atmosphere. That's the idea that we're going to use to begin exploring other planets. So here's kind of the task for today. These are the big three things I want to make sure you don't leave without me covering, okay? The first is I want to describe the methods by which we find and characterize planets. You have to know how we're actually doing it to understand what we can measure and what we can't measure. Then I want to get to describing our current state of knowledge of Earth-like planets. What have we actually learned? And it is amazing to think, if I had given this talk a year ago, how much less I would have been able to tell you. How much has happened really just in the last 12 months. And then at the end, we're going to talk about the first opportunity for really going and actually not just finding Earth-like planets, but actually planets that actually have life on them, and how we would actually make that inference. So the methods. Let's start with the methods, right? Okay. So we're going to talk about one way to find planets, and that's called the Doppler method, or the radial velocity method, or the wobble method. And the basic idea is the following. The star is not stationary. The star and the planet actually orbit each other. The star doesn't move very much because it's much more massive. So picture it as like two dance partners. There are two dance partners holding hands, but one dance partner weighs 300,000 times more than the other dance partner. Okay, so one partner's being really swung around. That's the planet. The trouble is the planets don't put out light, so you don't see that. But you do see this one dance partner that's kind of, and what you can measure is that the star is changing speed. It's sometimes coming towards you and sometimes receding, and that's periodic. And that's the way that we can find planets. And in particular, because the mass of the planet affects how much it changes the speed of the star, we can deduce the mass of the planet this way. Okay, got it? That's method number one. Method number two is the transit method, and that's the Venus idea we talked about. The planet goes in front of the star. Unlike the case for Venus, we don't actually get to take a picture and see a black dot in front of a resolved star, but we can measure the total brightness of the star, and we can see that the star is fainter when the planet's in front. And big planets block more light. So by measuring how much light is blocked, we can deduce how big the planet is. And then we can put those ideas together. Okay? So if the planet is a sphere, and we know the mass of the sphere, and we know the size of the sphere, we can figure out the density without any assumptions. Very simple, very simple idea. Really hard to do, by the way, but very simple idea. And then you can get the density. And of course, if the density is the same as, say, hydrogen, then the planet might be made of hydrogen. If the density is much higher, similar to that of rock, maybe we found a rocky planet. Okay? All right. So those are the principal methods. Now, the other thing that transits do is they allow us to probe the atmosphere. Okay? So the planet will pass in front of the star, and what's going to happen is that some of the light from the star is going to go through the atmosphere of the planet during those few hours, and then it's going to travel through space, and you're going to detect it with your telescope. And then you can see that during these times of transit, the chemical fingerprints of whatever molecules or atoms or clouds or the conditions are in the atmosphere are captured by that light as it passed through the atmosphere. And like fingerprints, we can then look at that light and say, oh, there's water, or there's methane, or there's whatever gases are present in the atmosphere of the planet. Okay? Now, this idea of transiting planets has really taken off. So in 2001, okay, we knew of one such planet. There was one planet outside the solar system that actually made these transits. And now in 2018, there's more than 5,000 such planets. Okay? So it really is a special moment in human history. How will studying the atmosphere tell us that there's life? Right? Well, if you were an alien astronomer doing this experiment on the planets of the solar system, you would see that there's something really special and different about the third planet from the sun. Okay? And that's because life has radically changed the content of our atmosphere. And for example, one of the things life has done is produced a lot of oxygen, right? It's a waste product for plants. It's unintentional, getting back to this idea of should we be listening for radio signals. Here, we're going to try to detect life through the unintentional waste products that are just produced as life goes about its business, okay? So life is going to change the chemical content of the atmosphere. We now have a way to study the atmosphere by the passage of light through that atmosphere. And this process has been going on throughout the 4.5 billion years of the Earth's history. Okay, so to make these measurements, we're going to need really, really powerful observatories. Okay? You can think about how big the sun was and how small the Earth was. And now we're not just trying to detect the Earth, but actually just detect the little onion skin of atmosphere, the thin atmosphere just surrounding the tiny dot of the Earth. And you can imagine it's a really difficult measurement to make. So it takes big telescopes. Fortunately, we are, as a national community, we are, with the astronomers and NASA, are building an incredibly powerful observatory that we hope will launch in 2021. That's the James Webb Space Telescope. Okay? So you might have heard about this in the news. It has been delayed, and it is over budget. And I am frustrated. It should not be delayed and over budget. But nonetheless, we are very close to completing it, and this will revolutionize essentially all major branches of astrophysics. For us, for the exoplaneteers, it, of course, provides something essential. It's a large telescope, right? If you're looking for that little atmosphere just for those few hours that the planet's in front, you have to gather a lot of information. You have to gather a lot of light. And having a big telescope in space allows us to do that. Also, the James Webb Space Telescope is very sensitive to infrared light. Why do we like infrared light? Infrared is where all the molecules we want to study, okay, so methane and water, they all show their fingerprints in infrared light, right? The same reason we have the greenhouse effect, right? That's going on at infrared wavelengths, okay, because of CO2 and water. That's the same signals that we're trying to detect. So we have to have a large infrared space telescope, and that's exactly what the James Webb Space Telescope will be, okay? What about on, and I want to show you some update photos of James Webb, okay? So James Webb was assembled at the NASA Goddard Space Flight Center in Maryland, okay? And I got to see it just before it shipped out. The mirrors have this beautiful gold color because of those infrared wavelengths that they want to study. It was then shipped to Houston for testing. And here we can see the enormous chamber. This is what we have at NASA, are these enormous testing chambers, because of course we have to simulate the thermal changes that the telescope will experience in space, and we have to be able to put the telescope in a vacuum, just like it'll be in space, and if anything breaks, actually fix it without having to go up to space, okay? So these tests were done, and you can see there was a very careful measurement. Will it fit? I don't know if you are big into parallel parking, you know, but it barely fits, and indeed that's where the testing was done. So we hope very much that JWST will launch in the next couple of years. Now, on the ground, of course, we can build even bigger telescopes. And so there's a big effort in the United States to lead the construction of 2 giant telescopes, one in the northern hemisphere, one in the southern hemisphere. My institution, Harvard, is part of the effort to build the one in the southern hemisphere, which is called the Giant Magellan Telescope, okay? And it's an international effort, too. We have partners with Australia, we're in partnership with Korea, so these are big projects, and we need big international collaborations. This telescope, when it goes online, which we hope will be about 2023, will be the largest optical telescope ever constructed, okay? It's going to be enormous, and thus be able to gather an enormous amount of light and really be able to probe these exoplanet atmospheres. Just to show you how big it is, okay? So these are the mirrors that will go into the telescope. We have cast 5 of these 7 mirrors, okay? We've put them into the big molds with the glass, melted the glass. We do this under the football stadium at the University of Arizona, because that's the only place on campus that's big enough to actually house these sorts of mirrors. And you basically put in the glass and melt it, and you spin this entire dish, and that creates the shape that you want because the glass is a liquid. And then you cool it slowly over months so that it doesn't crack. When those mirrors are cast, they look like this. That's one of the mirrors, okay? That's this middle mirror with a donut in the middle, okay? That's what people are sitting on. It hasn't been polished yet, that's why it doesn't look silver, but that's the actual mirror. So we've cast 5 of these, and we're trying to build the other 2. Now, for perspective, right, remember I talked about the James Webb being much bigger than anything else we've launched in space. The James Webb mirror is 6.5 meters. That would fit tidally within one of these mirrors, okay? These are 8.5 meters, and so you can see how much bigger things can be on the ground. So here's the idea. So we have these unprecedented observatories that are being built. They're being built for general reasons in astrophysics. They do all sorts of things with galaxies and cosmology, okay? But for us, for studying exoplanet atmospheres, they do this really precious thing, which is finally they give us the sensitivity to actually study the atmospheres of planets. And so the idea is, working together, can these telescopes, like the Giant Magellan Telescope and the James Webb Space Telescope, allow us to get at these precious little atmospheres, okay? So, and the answer is, yes, they can. But there's only one little challenge, right? Which is we actually don't have the targets. We actually don't yet have the planets to point them at. So we're building these facilities. They're gonna come online in perhaps 3 to 5 years. But we better figure out, we better have the targets, the planets ready to go that we want to probe with them. So let's go back to talking about actually finding planets, okay? So I just wanted to remind you of the challenge. This is the sun and the Earth. Does everybody see the Earth? Earth? No, it's not. No, those are spots. Those are sunspots, which are much bigger than the Earth. Did you know that? The sunspots are bigger than the Earth? That's the Earth right there, I think. My eyesight's not great. Yep, that's it, right there. So that's the Earth. And so finding the Earth, like forget about just studying the atmosphere, but you can imagine seeing the fraction of light blocked. It's about 84 parts per million, tiny, tiny little signal as Earth-like planets go in front of their sun-like stars. That's how we're going to find these planets, okay? And so our field, there was a revolutionary experiment in our field that actually kind of opened the treasure chest and moved us from studying big planets, which we'd been studying Jupiters, and that story about the parking lot. That was the reason we could do that from the ground with a small telescope. That was a big Jupiter-sized planet. But to study these small rocky planets, we really needed a powerful new tool. And that was the NASA Kepler mission. Okay? And it's really difficult to overstate the impact of Kepler on the field of exoplanets. Kepler is a telescope that looked at one patch of the sky. It looked at the same 150,000 stars for 4 years uninterrupted. Why 4 years? Because the Earth-like planets take a year to go around, and you want to see several of those passages to convince yourself there really is a planet. So it had to be able to look at the same stars for at least 3 to 4 years, and that's what it did. Okay? Then in about 2013, one of the devices inside the telescope that allowed it to point accurately failed. It broke, but the telescope was still operating, and so it moved to a new mission, which is still to find planets, but not those kind of Earth-like planets around sun-like stars that we've been talking about. So the main data came in between 2009 and 2013. And this is just showing you the actual launch. There's the spacecraft, and that's the actual digital camera that we used. This is what it means to find an exoplanet. These are what the data look like. Okay? So here I'm plotting as a function of time in days. Okay? So 200 days, 400 days, 600 days, 800 days. So several years of data. Got it? Okay? And I'm plotting the brightness of one star. Kepler, there's 150,000 of these light curves. I wasn't going to show you 150,000. I'll just show you the one. Okay? And you can see that mostly there's not much going on. Okay? The star doesn't change the brightness. There's these gaps. You see these gaps? That's just when the spacecraft stopped gathering data for a moment. Maybe it was downlinking its data, but nothing surprising. And then is there anything else in this light curve of note? Yes! What are these guys? Right? So what these are moments when the star suddenly gets fainter for a few hours, and then it returns to its brightness. And that's the passage of a planet in front of the star. Okay? And so you don't need a computer to find those, and so you can basically say, oh, I can measure the orbital period, the year for that planet, and then you can cut the data up into chunks and fold it over, and you can see this very nice signal. So if I zoom in on each of these and I plot them over on top of each other, I get this. Okay, so that's what it looks like for a planet to go in front of the star. But with a computer, you can dig down more into the noise and ask, are there other periodic signals? And the answer is yes, there are. There's another one. Here's another one. Okay? Here's another one right here. And this signal is buried down in the noise. You really can't see that one with your eye. Okay? And this was just one of thousands of exoplanet discoveries. So in this case, you've got 2 planets going around the same star. One of the planets is big because it blocks a lot of light. One of the planets is small. Okay? So that's illustrative. Now, Kepler found all sorts of planets. Okay? Hot Jupiters and mini Neptunes and super Earths, and we had to actually invent all sorts of new words because a lot of the planets were unlike anything we'd found in the solar system. Okay? And that was one of the big surprises. But what we, of course, really wanted to know was how common were Earth-like planets. Okay, planets that were roughly the same size as the Earth and the same temperature as the Earth. And so what that means is we want planets to be in what we call the habitable zone. So the habitable zone is like the Goldilocks zone. Okay, so the idea is if you take the planet, you make the planet, planet's got water, among other things, but it ends up too close to the star, then the water is a gas, right? So the water evaporates, not habitable, okay? Or if the planet is too cold, then the oceans freeze, okay? And so again, you don't have a habitable world. So you need to be just in this intermediate zone. And so I had the pleasure a few years ago of working with a graduate student named Courtney Dressing. And Courtney wanted to know what is the rate of occurrence for the typical star in the galaxy. How often do they host a planet that's the same size and same temperature, i.e. rocky, and would have liquid water on its surface as the Earth? And Courtney was the first human, I believe, was the first human to ever know the answer to that question, thanks to the use of the Kepler data. Okay? And the answer really mattered a lot to us because if the answer could have been 1 in a million, right? Maybe those planets are really rare. If it's 1 in a million, then the impact is that if you want to find the closest one to us, right? So the Kepler stars, we are not going to study these planets in detail. Kepler looked at a group of stars that were actually quite far away, so it was good at telling us statistics, but we can't study those planets in detail anyway. But if we wanted to find the closest example of that population and study it, but the rate of occurrence is 1 in a million, that means we would still have to look so far away that there was no hope of actually scrutinizing that planet in detail. If, on the other hand, the rate of occurrence was relatively high, it would mean that there was a path forward. And so, Courtney very carefully had to do a lot of work to do this calculation, to actually measure the sizes of the stars and therefore the size of the planets. And she arrived at the answer. And the answer is 1 in 4, okay? 1 in 4. So 1 in 4 typical stars in the galaxy has a planet that's, we think, broadly speaking, what we would call habitable, okay? And Courtney has done quite well. She's now a professor at Berkeley, which is a small technical college, I think. Okay, so, all right. So now, if we want to really get at the atmospheres, okay, then what's the challenge, okay? So the challenge is we need stars that are not too far away, okay? As things are closer to us, they are brighter, okay? So we need the closest possible stars, and our ability to study the atmospheres is limited by the fact that many of the targets we want to study are simply too far away. So we need to be able to look at the closest stars. And the size of the star compared to the planet really matters. Okay? So you remember, if we have a really big star, then the planet is tiny, the atmosphere is really tiny. It's really hard to scrutinize the atmosphere. If somehow we could magically make the problem easier, then we should do that, because it'll give us access with the same size telescope to more planetary atmospheres. So I often tell the story that in high school, I was told a terrible lie. I hope you've never lied to by your teachers. I was lied to by my teachers. I was told that the sun is an average star. Were you ever told this? All right, so it's a big fat lie. The sun is not an average star. The sun is a freak. The sun is much bigger and more massive and more luminous, puts out a lot more energy than the typical star in the galaxy, okay? So the typical star in the galaxy is what we call a red dwarf, one of these red dwarf stars. And compared to the sun, they're about 1/4 the size of the sun, maybe 1/4 the mass of the sun. And they only put about 1/1000th the amount of energy per unit time that the sun does. So they're like these little Christmas tree lights, okay, that are populating the galaxy. So that's the typical kind of star. The sun is actually a very strange star. Now, if you're willing to be open-minded, and I advocate, since we know nothing about life in the universe, we should cast a wide net. What would the habitable zone look like around these M-dwarf stars? Okay, and so drawn to scale, right? The idea of the habitable zone is the following. So here's a sun. Here's the sun. And, if you're too close to the sun, then water boils. And if you're too far away, water freezes. But there's some range of distances, okay, around the sun where you can put your planet and water is going to be liquid. For these M-dwarf stars, these red dwarf stars, okay, that zone is shrunken in because they put out a lot less energy. So it's like if I turn on a heater, turn on a light, and I stand at a certain distance and I'm comfortable, and now I turn that down by a factor of 1,000, you imagine you'd want to stand a lot closer before you find the place where you're comfortable once again. And that's exactly what that blue region, that's the Goldilocks zone around these M-dwarf stars. Okay? So that's a benefit for planet hunters. And the reason is that to be in the habitable zone or on a sun-like star, basically it takes a year for you to orbit your star. So if we're doing a transit search, if we're looking for these eclipses, we have to wait a year between events. But now, if the habitable zone is shrunken and close, then you only have to wait 10 days. The planets only take 10 days to go around their stars. And so that's a huge perk because we can get the job done in much less time. The other interesting thing to note about these red dwarfs is how populous they are, okay, how common they are. So if I take a small part of the galaxy and I draw a bubble around the sun, and I count up all the stars in that bubble. And I'm going to go out to 10 parsecs. Okay, so that's just like the local, like Millennium Falcon kind of distance, right? That's whatever that really means. That the tiny, tiny volume of space, and I count up all the stars. That's about, 30 light years, 33 light years. Okay, it's very interesting to ask, what kind of stars do you encounter? So it's very interesting. There's 20 white dwarfs. White dwarfs are the dead corpses of sun-like stars. And once they die, they don't go away. They just stay there. So over time, these have accumulated. So there's kind of this graveyard around. And there's 20 of those guys. And then we give stars, and this is a Harvard invention. We give them a very complicated letter name that doesn't mean much. So sorry, but we call the very massive, the really bright stars, we call them O stars and B stars. There's none of those. But if you go down to what we call G stars, that's the sun. The sun is called the G star. There's 20 of those in this volume of space. Okay? The question is how many red dwarfs are there in the same volume of space? So let's have a look. There they are. Okay. So there's 20 G dwarfs, but there are 246 M dwarfs. Okay? So they outnumber us 12 to 1. So if they make planets, and they make planets the same size as the Earth and the same temperature, and they do, because that's what Courtney told us, then surely they're an interesting place to go and actually look for whether there's actually life on those planets. Okay? So that's what I set out to do in a project called the MEarth Project. Okay? So the idea, why do we call it MEarth? Because we're looking for Earth-like planets around M dwarfs, right? MEarth. Also, it makes us happy. MEarth, happy? Good? You're with me? Okay, happy. And so what is MEarth? So MEarth is a collection of robotic telescopes, okay? So it's 8 robotic telescopes in Arizona and 8 robotic telescopes in Chile. And why do we have robotic telescopes? That's because we want to find planets that go in front of, that eclipse these nearby M dwarfs. So they're all over, like we're in the middle of a swarm of these M dwarf stars. They're all around us. And so they're in every direction. So I need a whole bunch of telescopes because I need to be able to take a telescope and say, look at star number 1, and then look at star number 2 and star number 3, and repeat that while we're waiting for these eclipses to occur. Okay, I can't just do it with one telescope. So here's another view of the observatory. This is the observatory in Chile. Okay, so there they are. They're each 16 inches. In the mirror is about 16 inches. So if I were to stand next to these telescopes, they'd sort of be my height. Okay, so they're relatively modest in size. And then they're located some in the north and some in the south. So why do we do that? Because could be that the closest aliens to us are in the southern hemisphere or in the northern hemisphere. We need to look at all this. We can't just look at half the sky. Okay, that's why we had to build 2 observatories. And then I wanted to show you a time-lapse movie of the observatory in operation. Okay, so the observatory runs every night. Should be running tonight. And this is what it looks like. Okay. So these are the telescopes that are frantically searching the different stars. Now, this telescope is looking at 20 different stars, but I'm just going to plot the data from one particular star, and this is just on one night. And so it's measuring the star. This is the brightness of the star. It doesn't look very interesting. Oh, this telescope has suddenly noticed that that point is lower than these points. So the star is suddenly fainter. So the telescope stops what it's doing. It stops its survey mode, and it stares at that one star until that star brightens up again. And then it goes back to its observing. So this happens in real time, okay? And this is great. I'm home with my family. It's robotic. You know, I can have a beer. Great. We can hang out. My 4 daughters all play hockey. I'm their hockey coach, so that's a lot of fun. And then the observatory goes and finds the planet. I want to pause and say this is all due to the incredibly hard work of the project scientist, a guy named Jonathan Irwin. He is the maestro that makes this happen and has really, constructed MEarth and created the data analysis pipeline, and also gets to send me the cool email saying, we got one, and that's what happened when we found this planet. So we have found a number of planets over the years. I want to tell you about one of them, okay, and that's the discovery of a temperate, meaning sort of Earth temperature, rocky planet transiting a nearby star. Okay, and at the time, it was the first planet. That was the first such planet where we knew it was the same temperature as the Earth, and we knew it was rocky. We actually knew it was rocky, okay? And so there was this totally unremarkable anonymous star. It was so anonymous it had this catalog name, LHS 1140, okay? boring name, okay? And it was one of the 2,000 stars that we were searching, and all of a sudden we noticed that it got fainter by about 0.5%, so just a tiny change in brightness, okay? And we saw this one event, like I showed you in the movie. We saw this one event, and then we kept looking at the star, but it didn't recur. We didn't see another transit. So we thought, did we get it wrong? And what we instead did is we went and used that other method. We started the Doppler. Remember I talked about the dance partners? So we went back and did the Doppler monitoring, and we could see that the star was changing its velocity. The star was changing its speed, coming towards us and going away from us, but on a much longer time scale than we had thought. Normally we find planets that go around the star every day or two. This planet took 25 days to go around, and that meant it was going to be a relatively cool planet, not a super hot Earth. Okay? And so indeed, we have discovered this planet. It's got a terrible name. If the star is called, so in astronomy, when we find a planet around a star, we take the name of the star, which in this case is LHS 1140, and the planet is LHS 1140b. Isn't that awful? It's awful. It's really awful. So the planet is a little bit bigger than the Earth, okay, 40% bigger than the Earth. And just to show you to scale what this looks like, if that's the sun, okay, that's the star. That's not the planet. That's the star, the little red dwarf. And then that's the planet right there, okay? And then we measured the wobble. That's the wobble that tells us the mass of the planet, and that allowed us to determine it really was rocky. And then I can draw the entire system to scale, okay? So everything is drawn to scale. That's the distance between the star and the planet. That's the size of the star at that same distance. And here's the little planet over there. And it's far enough away that this planet gets only about half the amount of energy that the Earth gets, which actually means it's squarely in the habitable zone. Okay, so if you look at our solar system, the Earth is kind of at the inner edge of the habitable zone. If you're a little bit closer, we don't think the Earth would be habitable, right? Venus is not habitable, but the Earth could be a little bit farther away, and particularly for these red dwarfs, you can get a little bit less energy. So there's a habitable planet. Okay, now just recently, like just in the past few weeks, something interesting happened with this star. So we, after we'd found this planet, we went and used the NASA Spitzer Space Telescope, okay? And so that's an infrared observatory that can stare uninterrupted at stars, and it's really good at making light curves. And we were monitoring, we knew, once we figured out when these transits were happening, we were using that observatory every 25 days to go and observe the next transit, just to see if anything interesting showed up, okay? And so here's one of those data sets. Okay, so this is the eclipse, right? So the star is bumping along, and then it goes down. That's the expected planet going in front of the star. These data are very high quality because it's now being gathered in space, and then it brightens back up again. At the time that we were doing this, a new graduate student, a guy named Christo showed up and was working with me, and he was very excited. He'd heard about machine learning. He said, I've heard machine learning is cool, and I want to use machine learning, but for astronomy. I said, okay, sounds great. So he went and took this really hard computer science course, and for his final project, he was able to use the MEarth data and actually do a machine learning project. And he said, I think I found a planet. I think I found another, and I said, well, really, what star? And he said, well, it's the star that you already have a planet about. And I said, no, Christo, I know you're a new grad student. It's exciting, you know. Yeah, we actually do in the community. We call it planet fever. Like people get that excitement, but then as they look at the data, it goes away, right? And he said, no, I'm pretty sure. And so I said, well, go talk to this guy, Jason Dittman, who had been a previously graduate student, but was now working over at MIT as a postdoc, because he has the Spitzer program. And Christo walked in, and Jason said, damn it, I knew that was a planet. Right? And there's the other planet. So they had independently discovered a second planet in the same system. And just to show you what you're looking at here, this is confusing, right? So the star is first passed by the big planet, the one we knew about, okay? But then it so happens, at the time of these data were gathered, a second smaller planet also passed in front of the star. You can tell it's smaller because it blocks less light, right? That's the first planet. It blocks 0.5%. This guy only blocks maybe 0.25%, so it's a smaller planet, right? And also this planet is orbiting interior to the known planet. How do you know that? Because the duration is shorter, right? If this planet takes several hours to go in front of the star, this planet only takes about 45 minutes, so it must be going at a higher velocity. And you do that if you're orbiting a star, you go around faster the closer you are. Okay? So what was so exciting is now we had this rocky planet system, right? So there's the star, there's the planet that we think is in the habitable zone, LHS 1140b. And sure enough, you find another planet. What exciting name do you think we give it? LHS 1140c. But what's so exciting is basically you have this family of rocky planets. Okay? So this really starts to look and feel like the inner part of our own solar system, right? Multiple planets, they're all in the same orbital plane, and they are similar in size to the Earth. Some are hot, and some are a little bit cooler. Okay? Okay, so where do we go from here? So we're going to continue to operate MEarth, but a number of us realized, really probably about a decade ago, that what we needed was a new space telescope. And that space telescope was going to take the discoveries of the Kepler mission. Kepler told us the rate of occurrence of planets, but actually find the very closest examples. Kepler, like I said, it isn't looking at the closest stars. It was looking at a certain group of stars that were very far away, because it just looked at one patch of the sky. We needed a new observatory that could scour the whole sky from space and find all the very best small rocky planets. Okay? And so that's called the NASA TESS mission. Okay? So I'm a co-investigator on TESS. TESS, our mission is to find hundreds of nearby small planets amenable to detailed characterization. So these are going to be the very bestest, closest, rockiest planets. There are not going to be better planets. These are going to be the best planets, so that we can actually go and really characterize their atmospheres. This was led by a guy named George Ricker at MIT. And this is what the project looks like. Okay, so it's 4 camera lenses. And those former camera lenses are in the shroud here, and you can see humans for scale. So it's actually a relatively modest telescope, not very big. And in April, just this year, we got to launch pad, and we were delayed a couple days, and then we launched. So it was super exciting. That happens to correspond to spring vacation week in Boston. So my whole family went down, and we got to see this launch. And so there it is taking off. So TESS is just tiny. If you've never really kind of looked at rockets before, all of this is propellant. And then in this thing, TESS would be smaller. TESS would be about the size of the laser dot in there. So all of that is just to get you into space, but TESS is actually really small. Okay? So how does TESS look at the sky? Okay? So TESS has these 4 cameras. Okay, there's 4 cameras in there. And each camera has a very, very large field of view. Okay, each camera will look at 24 degrees by 24 degrees. So that's like really if you took your hands and held them apart, a couple hand width. That's the amount of sky they'd be blocking. So it's a huge part of the sky, a lot of stars in that part of the sky. And then the 4 cameras are pointed so that in one shot, it looks from the pole, it looks from what we call the ecliptic pole. So if you take the plane of the Earth's orbit, okay, the pole, if you look up towards the pole of that plane, then TESS looks from there all the way down in one single snapshot. And this is kind of what we call the TESS salute, because if you can kind of get your hands open enough, one camera points up and then the others work their way around. Okay? And that's in one snapshot. It looks in one part of the sky for about 28 days, and then it moves over to the adjacent sector. And so over the course of a year, it'll do 13 of these, and it'll make its way around. And then the telescope flips over, and it starts doing this in the northern hemisphere. So in 2 years, it surveys essentially the entire sky, okay, spending 28 days on each part. Of course, at the poles, right, where the same camera is not pointing at a new part of the sky, but actually just kind of rotating, you keep getting data. So actually, in some parts of the sky, we look for a year. So that means we can find longer period planets. But remember, I'm very interested in these M-dwarf planets, and their orbital periods are only like 10 or 20 days. So 28 days of data is already pretty good. So TESS launched in April, started science observations in like late August, and by beginning of September, we had the first planets. Okay, so and what I love about TESS is TESS, the data are public immediately. There's no proprietary period for the scientists who were involved in building TESS. Okay, so it's a NASA-funded mission. Sometimes with NASA missions, the scientists basically for all their hard work. They get a year or two to look at the data before it goes public. Here, the data go public right away. So if if anyone's interested, right now what we're trying to do is standardize the pipeline to release those data. But once that happens, any of you can look for planets just as I do. You can download the data on your computer. You can look for these signals. I kid you not. And you can be the first to see those planets. It's totally open. Okay, and so here's one of the first planets I'm very excited about. Again, there's the TESS light curve. You can see this eclipse. And it's an ultra short period terrestrial planet, meaning kind of rocky planet. Now, unlike the planet I told you about earlier, which was in the habitable zone, this planet is definitely not in the habitable zone. This planet goes around every half day, every 12 hours, 11 hours actually. It goes around its star. So it's a really roasted planet. But what's very exciting about this is we want to know, does this planet, because it's so hot, did it actually hold on to its atmosphere? Or did it lose its atmosphere? And Laura Kreidberg, she's a postdoc fellow at the Harvard Smithsonian, where I work, had a really great idea. She said, well, let's go and use that Spitzer Space Telescope, that infrared space telescope I told you about. And what we're going to do is we're going to just stare at the planet as the planet spins on its orbit. Because the planet is so close to the star, it's tidally locked, just like the moon is to the Earth. So as the planet goes around, it always presents the same face to the star, okay? And so what that means is if you forget about the star, you actually, over time, just get to see the planet turn on its orbit, okay? If the planet has no atmosphere, that means there's a scorching hot day side and an ice cold night side. And if you look in the infrared, that means when you look at the day side, the planet's really bright, and then it gets really dark as you look at the cold night side. If, on the other hand, the planet has an atmosphere, then there is no such day-night variation, or at least much less. So what that means is, and so she wrote this proposal, and I said, Laura, no, they're not going to give you 100 hours for that idea. They're almost wrapping up the Spitzer mission. Anyway, of course, she wrote it, and she got the time. And so in December, we're going to get those data. And yeah, don't listen. So we're going to get the data in December, and that'll be the first time. Yeah, that's the first time that we have a rocky planet orbiting another star, and we're going to actually know whether or not it has an atmosphere. So ultimately, we want to get to the point of looking for like oxygen, right, in the atmospheres of planets, and that will show us that there's life. But you can see how quickly this is proceeding. Only in the last year did we find the first examples of rocky habitable zone planets. Now by December, we're going to make the first study to establish whether or not a rocky planet has an atmosphere, and maybe on time scale 3 to 5 years, we can go and detect things like oxygen, which at least on the Earth are entirely produced by life. So I do want to kind of pause and point out that, individually, a large ground-based telescope or the James Webb Space Telescope cannot tell us that there's life on a planet. And this is important to understand, okay? And the reason is that they're sensitive to different molecules. So the Giant Magellan Telescope, okay, the Giant Magellan Telescope, it's actually a great way to go and detect oxygen. And oxygen is very precious because on the Earth, oxygen really is all produced by life. But if you just have oxygen, you can't say that there's life because we can hypothesize, it's not what happens on the Earth, but we can hypothesize that there are other ways to make oxygen in an atmosphere. One is if you have UV light shining on water and the water disassociates, okay, water is H2O. If you knock off the hydrogen and send it off to space, you're just left with O2 combined to make the O2. The oxygen's left, and that would be a way to make oxygen that has nothing to do with life. There's other ideas about how to make oxygen. So you have to do more, and what you need to do is with James Webb, you can detect methane and carbon monoxide and carbon dioxide that puts that oxygen in context, okay? So the idea is together they can get the data that will allow us to conclude that there really is life. The GMT, these large ground-based telescopes that can search for oxygen, and the JWST can put that in context and tell us whether the only plausible explanation for that oxygen really is due to biological activity. So that's the vision for finding life on other planets, okay? It's not spaceships, it's not SETI, it's this very practical approach of looking for what the Earth is, the Earth is broadcasting to space all the time the presence of life through the chemical signatures in our atmosphere. And we should go and do the same thing and look at other alien atmospheres. So, kind of to step back, I think it's really, astronomy is a very special field, right? we don't often generate a lot of practical goods for society, right? I really admire my colleagues who work in the life sciences and are trying to rid us of the scourge of disease, or some of my colleagues who work in engineering and really are making our lives better and more enjoyable through technical innovations. What does astronomy do? I would say astronomy really is great about allowing us to get at some of the really profound questions, which I started by telling you have been with us for as long as we've been writing down our ideas, okay? And so the connection I'm trying to make here is that, these new observatories, those are like our spaceships. These observatories, they allow us to see what these planets look like, to imagine that we stand there, to actually identify the conditions on the planets and really ask whether or not they have life. So with these new observatories, I think we may make the first discovery of life on a planet other than the Earth. And the impact of that is really well beyond astronomy and even science. I think the impact really will change how we and our children kind of view their places in the cosmos. So the best part of my job is that I get to work with these amazing students from around the world. And in visiting the university here for the last couple days, I can see that like joy in my fellow professors here, right, where they're just working with these amazing students at the University of Washington. And so before giving a public talk, I wrote a number of my students and I said, look, tell me what what are these new powerful observatories? What does that mean for you, thinking about the future? And so these are some of my former students and what they wrote back. Okay, so this is Heather Knutson. Heather was a graduate student with me. She's now a tenured professor at Caltech. And here's what she said. She said, there's nothing like staying up all night on top of a mountain to observe a new planet. You can walk outside and say, there it is, that star. We're exploring new worlds and traveling to a distant mountaintop to use one of the world's largest telescopes as part of that process of exploration. So for us, the telescopes really are like these spaceships. They really are this magical way to travel to distant worlds. And if you've never gone to an astronomical observatory and spent the night there, it'll blow your mind. It is magical to be that close to the stars. This is Elizabeth Newton. Elizabeth just moved October 1st to Dartmouth, where she's starting a professorship there. She said, because I asked her, she was always complaining about the weather in Boston, and she said, look, when we look up at the night sky from Boston, you see maybe a dozen stars, but if you go somewhere where it's really dark, you'll see thousands. But that's just a small fraction of what's out there. Using an astronomer's tools gives us a new way to look at the night sky. So these were students from a few years ago. And then one of my current graduate students, Hannah Diamond Lowe, she wrote back with a great answer. So I wanted to share this. I want to share this excitement that these students feel. And what Hannah said was, she was down observing actually at the Magellan observatories, twin telescopes in Chile, which I'm showing here. These are the Magellan telescopes. And she said, spending time at one of the biggest telescopes in the world has given me a grand perspective on the accomplishments of humanity. From this vantage point, detecting signs of extraterrestrial life seems well within our reach. There's Hannah. So, what's amazing to me, like I don't think of myself as being very old, okay? I'm really old for the field of exoplanets. But when I started graduate school, just detecting like a Jupiter seemed outlandish. And here's a student only, when did I do graduate school? So like not even 20 years later. And for her, the idea of what I just told you about, of actually going and looking for life through our telescopes seems entirely reasonable. Okay. I really want to thank the funding that has made all this work possible. There's a lot of work that's gone on, and I was kind of just hitting the high points. I do want to point out what has been essential in astronomy is having funding from both the federal agencies and from private donors and from private foundations. And so this work was supported by the National Science Foundation and by NASA, but also by the David and Lucille Packard Foundation and the John Templeton Foundation. And I didn't do this work. I didn't do this work. I get to work with the most amazing people, and these are their names: Zachary Berta-Thompson, Jason Dittman, Courtney Dressing, Raphael Haywood, Jonathan Irwin, Mercedes Lopez Morales, Christo Ment, Elizabeth Newton, Joey Rodriguez, who's given the colloquium on Wednesday, I think, and Jennifer Winters. I was showing you their work. Okay, so to wrap up, okay, so this is stuff you want to be talking about at breakfast tomorrow, okay? Yes, this is what you're going to talk about, or tonight even, but these are the high points. Okay, so the big takeaways, right? Big discoveries, red dwarfs are the most common star in the galaxy by a long shot, and there's at least one habitable planet for every 4 red dwarfs. That's number one. Number two, we have begun to find the closest transiting Earths, okay? And we're planning to study their atmospheres with the next generation of powerful telescopes. So just in the last year, we have found examples of these habitable rocky planets, and we are building currently the observatories that will allow us to get at their atmospheres. And number three, the search for atmospheric biomarkers such as oxygen will be humanity's first attempt to really answer this great question about whether or not we are alone. Okay, with that, I want to thank you and ask if you have any questions.
Okay, so now it's time for David to take questions from the audience. We have 2 microphones at the sides of the room, so if you have a question, I would like to invite you to line up at the microphones. We have plenty of time for questions. And we'll just go back and forth, so you can start.
Hi. So you're saying that the 1 in 4 for the red dwarfs, but are the orbital planes always in line with our viewing? I mean, aren't
Great
some of them
question.
this way?
Right. So 1 in 4 of these red dwarf stars has such a planet. Does that mean that 1 in 4 transit? The answer is no. So only about 1 in 50 transit. So only 1 in 200 or so will actually have the planet and show it to us. So that's right. So most of them don't eclipse, but the subset that does, that's the ones where we're going to do these observations. Yeah. And in fact, recently we discovered, not we, but the community discovered that the closest star to us, which is a red dwarf, which is called Proxima, has a planet. It doesn't look like it transits, but it has one of these planets. So they really are very common.
The planet that had the sexy name,
Right.
how far away is that planet? What's the distance?
Oh, so that's 12 parsecs away. So that's really close. So they.
What's that mean? I don't know what a parsec is.
Right. So that's
Parsec's 3 light.
yeah, like right. So like 35 light years, 40 light years. But the very, I mean, that's basically. Okay. So if I shrunk the entire galaxy, if I took the entire galaxy, and I shrunk that down to the size of the United States. Okay, so like Los Angeles to Boston, that's one edge of the galaxy to the other. That planet would be like walking across Central Park in New York. That's how close it is to us, the distance across Central Park compared to the distance across the United States.
I've heard the prospects for finding habitable planets around red dwarfs criticized on...
What?
This is on the basis that because...
These questions are supposed to be monitored.
Oh. That because red dwarfs are very volatile stars and planets in the habitable zone are very close to them, that solar flares from red dwarfs would likely strip them of their atmospheres. What reason is there to believe that a planet in the habitable zone around a red dwarf can sustain an atmosphere?
Yeah, that's a great question. So, red dwarfs make planets. They've got planets that are the same size and temperature as the Earth. Are they good parents? Do they actually allow those planets to flourish? So they have been much maligned over the years. It is true. Red dwarfs have personality, and they do have large flares and ultraviolet light. I do want to point out that actually one of the centers of excellence for actually understanding exactly that question is the University of Washington. That the astrobiology group here really is leading the charge on understanding exactly those kinds of questions. Does it mean they lose their atmospheres, or if they do keep the atmospheres, it's still not hospitable? And a lot of my answer I'm about to tell you comes from their research. Yes, I'd say it was common wisdom like 34 years ago that you shouldn't look at red dwarfs. But no, the answer is when we look in detail at red dwarfs, they actually don't flare as much as people had thought. And actually, once they're relatively old, they calm down, they never flare, they spin very slowly, and they have very little UV light. So actually, once they're moderately old, they're very, very quiet. That star that I was telling you about, LHS 1140, our sun spins every 25 days. That star spins every 130 days. That's how calm it is. And it never, in the entire 4 years we've been looking at it, it never has had a flare. So M dwarfs get a bad reputation. But when they're young, they do flare. And the question is, can the planets survive this kind of turbulent youth and still then emerge to being habitable? And we don't know. And so ultimately, I would say it's a great thing to be worried about. We need to go do the experiment. And sadly, we might learn that they don't allow life. But it is where we should begin looking, because that's currently where we can look. Next, we're on this side, yeah.
If you were a betting man, how long do you think it will be before we find one? How long do you think it'll take?
So I'm not a betting man. All right, so next question. No, so it's a great question. Of course, that's what keeps me up at night, like literally, because I'm an astronomer, it keeps me up at night. I would say I think many astronomers will concede one opinion or the other. I actually am open-minded. I actually think that we may find the first planet we look at where we actually have the sensitivity, we could find life. And basically, there's lots of reasons to think that life is very robust. Once you have roughly the right chemical mixture of elements, you've got sort of the right temperature, you've got liquid water. I mean, look how quickly life took hold in the Earth. Life is inevitable. On the other hand, I wouldn't be surprised that we look at 10 and then 20 and then 100 of these exoplanets and don't find life and learn that life was a very rare event on the Earth. Importantly, it's not the case, often people get into an argument about numbers. And they say, well, there's 300 billion stars in the galaxy, and there's 300 billion galaxies, so then the probability would have to be like vanishingly small for there not to be life. That's not a good argument to me because I need to be able to measure it. And so my observable universe is not 300 billion. It's just the local region of space where my telescopes can actually probe. And so in that case, it's only thousands of stars. So we really might find that among the closest 10,000 stars or even 500 stars, whatever it is, that there just isn't one with life on it. And so we are effectively alone. Yeah.
I realize it's not your area of expertise, but are there opportunities to find signs of life in our own solar system? And are people looking?
So the great thing about being a Harvard professor is I can speak forcefully about things that are not my area of expertise. So I think that so it's a fascinating question. I think that, of course, a big part of what NASA does, so astrophysics is just one quadrant of NASA. And a lot of our effort to explore the solar system, of course, is led by NASA. So yes, there are very exciting opportunities to look for life on Titan is one idea. That's a moon of Saturn, or Enceladus, or Europa. So Europa is a moon, one of the big moons of Jupiter, where we know that there's liquid water under a fairly thick ice layer, several miles. Missions are proposed and debated. The difference is that if there is life, it's very different than life on the Earth. So it could be that there's life there, but it's, what we're interested in is like life that's so prevalent, it's radically changed the surface of the Earth. I mean, if you're an alien looking at the Earth, the continents are green instead of brown. Like life is complete, as the most active molecule in the atmosphere is oxygen. It's made by life. When you're going out into the solar system, we know that life is not abundant anywhere else. Could it be hiding in a little crevasse or something? Yeah, maybe, but we have to design experiments that can find life that's quite different. So we don't know, and we should definitely look. And that's why I would advocate both approaches. We should look within the solar system for life that's very different, and we should look outside the solar system for life that's very much like life on the Earth, because we would know how to recognize it.
Yeah. Could you talk about observing the reflected light from these transiting exoplanets as they pass behind the star?
Yeah, sure. So my first project in graduate school was to actually look for reflected light, look for the light bouncing off a planet. And in that case, it was actually because when these signals were first discovered, this wobble signal, there was a big debate, and some astronomers said those are not planets. That's a kind of stellar pulsation, and we've just been fooled. And finally, reflected light would prove it. And actually, I was tortured by this because I lived in a big student co-op. I lived with 20 other students, and every day we'd all cook dinner together. And I'd come home, and they knew I was looking for reflected light, and they'd say, "Dave, did you find the planet?" And I'd say, "No." And they'd all laugh. They'd be like, "Ah, ha, 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 ha." And then we'd have dinner, and I'd go to bed and get up and do the same thing. It was 15 years later that somebody measured the reflected light, and it just required much more powerful telescopes. So yes, we absolutely do. We see the reflected light spectra. We see light bouncing off the planets, and that's interesting because it tells you about the scattering in the atmosphere. We also, the related idea is we see the thermal emissions. So the idea is instead of the planet going in front, when the planet goes behind in the infrared, its light disappears. So there's a moment of time where you just get to see the star. And then when they're both in view, you get the light together. But if you subtract them, the light from the star goes away, right? Because it's in both those images. And you're just left with the light of the planet. And that's a well-established technique to actually get the emergent spectrum of the planet. So we have many different ways to get in the atmosphere. The one I highlighted in the talk was the transmission, but you're exactly right. The passage of the planet behind the star gives another opportunity. And of course, most planets that go in front of the stars also go behind the stars, so they're complementary. They don't always. They actually, the orbits don't have to be that way, but mostly they do. So, yeah.
I've read stories about like the Watson supercomputer, and people are like, "Oh, it's better at identifying tumors than professional cancer doctors." If it's not already, do you think a similar kind of AI could be applied to finding exoplanets?
Oh, great question. So it's certainly true that there's been a lot of innovation in computational techniques, and we have profited from that, and sometimes we've been the innovators. We do use supercomputers. In the case of Kepler, there was a postdoc working with me, a guy named François Frassin, and one of the tricks with these planets is that when you're looking and you see a blip, instead of it being a planet going in front of a star, it can be this tricky system that fools you, where basically you're an eclipsing binary of two stars that go in front of each other. But there's a third star along the line of sight, and all that light gets mixed together, and the eclipse gets diluted. And the way you rule those out is you have to basically consider the universe of possibilities of those and weight the probabilities. And so basically we use the supercomputers at NASA Ames Research Center in the Bay Area to answer those questions. So we do use a lot of these innovative techniques in trying to process our data. And they do find planets that I think the human eye misses all the time. Yeah.
Thank you.
Minor point, but then I couldn't figure out why you knew that those planets 1140 B and C were in the same orbital plane.
Right. So we can basically constrain that through really high quality data. You can tell the core. So basically, if you picture the star, and as you go across different lines I would draw across the star, the transit will last different durations of time. But there's another independent measure of how quickly the planet is moving, which is actually the ingress, this little brief moment where the planet gets onto the star and gets off the star. That gives you a separate measurement of how quickly the planet is moving. And so basically, once we model that data very carefully, it gives us uniquely what we call the inclination, the tippiness. And in that case, they're exactly aligned. Not all systems are. We see systems where the planets are misaligned. And in the solar system, some of the planets are a little bit misaligned. And that's really important. Those numbers are very important for understanding how the planets formed and how they evolved after they formed, basically whether they were stirred up or not. So.
Thank you.
So as someone who builds spaceships for a living, don't sell us short. We may get there yet. My serious question is this: as we're studying atmospheres, are we biased by the search for life, or will the study of atmospheres be essentially full spectrum, where we're looking to really understand the total composition of these planets' atmospheres?
Yeah. So on the spaceship question, again, I'm not saying we shouldn't pursue it. I'm just saying it's not the way to first find life. So I'm definitely not poo-pooing those ideas. Just that the way to do this stuff can come to fruition in 10 years, maybe less. and the spaceship thing will take longer. In terms of the atmospheres, so basically the studying the atmospheres of Earth-like planets is the hardest task, and so by creating that capability, we gain the capability to study other kinds of atmospheres. And so we have been for 15 years studying the atmospheres of gas giant planets across a wide wavelength range. There are many exciting, here I've chosen to focus on the search for life, but there's many, many exciting scientific questions that have to do with the physics of the atmospheres, how the atmospheres are produced, how the atmospheres are lost or retained, and all those, that sensitivity is going to be available to us as we push on this hardest thing, this kind of most demanding application. It kind of opens up all the other stuff for us. Yeah.
Thank you.
Are there any challenges with short period variable stars that have similar light curves to transits?
Yes. So stars are intrinsically variable, and in particular they have spots. And so, you know, in some of those, I can show you light curves where the stars are bouncing up and down. That's actually a positive because it tells us how quickly the star is spinning, so we actually get information. Fortunately, it never mimics a planetary eclipse. The planetary eclipse, the thing you realize is if this is the star, the planet goes in front, but it's only in eclipse about 1% of the time. The rest of the time, it's over here, it's over here, it's over here, it's over here, and the star looks flat. Whereas a spot is continuously varying. So even if they're at the same period, they have every single spot is going up and down all the time. This eclipse looks like nothing, 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 eclipse, nothing, 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 nothing. So fortunately, we don't get confused that way. Yeah.
So speaking of atmospheres, our planet is experiencing some issues with global warming. Has there been any studies about the effects of global warming with our surrounding environment, even though, you know, the planets are far away from us? Is it insignificant or nominal to where there might be some concerns or changes? And do we also monitor other planets that go through similar temperature changes?
Oh, I see. Yeah, so you're asking whether we think about those sorts of changes in the atmosphere as they apply to other planets? Or
Yes.
Is that what you're asking?
Yeah, what the effects are with global warming with our planet. Does it make a big difference for neighboring planets as a whole? Or is it so insignificant that it might not even make any difference?
Yeah, so I mean, certainly the composition of the Earth's atmosphere has changed dramatically, very slowly, but over time through life, but also through physical processes, through volcanoes and outgassing and so on. And we definitely, there have been very interesting papers written about whether you could see those. So that one of the benefits of astronomy is we can find Earth-like planets of different ages. So we can find planets around other stars, and we can guess the age of the star. And we can find Earth-like planets that are only 100 million years old, or that 1 billion years old, or 4.5 billion years old, or 10 billion years old. And we hoped by basically putting together this family, well, this kind of portrait of planets over time, we could actually see how these atmospheres vary. But global warming, of course, is a much more shorter time scale. That's a sort of 50-year time scale, and it definitely would produce observable effects, but they would be pretty catastrophic. They'd be very different.
Thank you.
So, how likely is it for us to find life as we know it, and how different could it be?
Yeah, great question. So thank you. So the strategy I'm outlining is basically that we look for life as we know it. And it's not, I'm not saying that other kinds of life can't exist. In fact, life could be extremely diverse throughout the galaxy. It's that I haven't been able to think of an experiment that would allow me to recognize that life. So I start with what I know. I start by saying, look, I understand the Earth system. I could recognize, I know what the combination of gases are that I have to detect. That would allow me to say, okay, that's also going on this other planet. I'm really hopeful that other future students like yourself are going to come up with those ideas about how do we actually now go and find other signatures of other kinds of life that isn't on the Earth, but we'd still feel confident that we'd be able to infer it based on data we can realistically get with our telescopes. Thank you.
Yes, you say habitable planet, and I'm just wondering if we were to stand on one of these planets, could you speculate on what the conditions would be like? Huge tides, a very dim star, maybe,
Right.
Ice, these kinds of things.
Yeah, so that's right. Habitable does not mean pleasant. You know, I mean, I grew up in Canada. It's in the habitable zone, sort of. But no, it's a great question. So that's right. So for these red dwarf stars, I think there would be a permanent day-night side. So on some parts of the planet, you would always see the sun, and on other parts of the planet, you would never see the sun. So that would be very different. The sun would be very red, so much more of the light comes out at redder wavelengths. There's still plenty of light to do things like photosynthesis. The overall amount of light wouldn't be any dimmer, right? The planet still gets the same amount of energy. It's just that more of that energy is at red or an infrared light as opposed to optical light. And the star would be bigger in the sky because we're close. Even though the star is smaller, we're actually quite close to it. The star is bigger in the sky, and so there would be quite a bit of different changes. So it's not necessarily a place that would be pleasant for humans, but it's a place that basically allows liquid water and therefore allows all the interesting chemistry to go on that we think was how life got started on the Earth. Yeah.
Recently, there has been news about a possible exomoon that has been discovered. What do you think are the implications of that, and how does it relate to possible, more like rocky moons in the future?
Yeah, that was just announced. So that's David Kipping. He's a professor at Columbia. He was a postdoc at the Harvard Smithsonian, and he worked on the moon problem for years. And so he's finally saying that he's got enough data to go forward. He himself is using kind of somewhat skeptical language. He's not saying this is a slam dunk. Basically, it's a somewhat weak signal in the data. And it's a strange moon. The moon itself would be the size of Neptune, and it orbits a Jupiter-like planet. So that's really unlike anything. The moons in our solar system are all very small compared to this sort of moon. But he believes he sees it in the original Kepler data and then as a follow-up in the Hubble Space Telescope data. So he's not saying this is absolutely certain, but it would be very exciting to find these moons for reasons that allow us to understand planet formation. So if you look in the solar system, the moons actually are great clues as to what happened in the late stages of formation of the solar system. But also, moons are very exciting because they could be abodes for life, right? So the way we talked about here to keep a planet warm is to have it close to the star. But of course, the other way to have liquid water is tidal heating of the moon. So the moons of Jupiter are very cold, but they have liquid water. One of them has liquid water because it's close to Jupiter and it gets squished and stretched all the time like silly putty. And so that generates enough heat that it can actually melt the ice. And so that's also a possible new kind of habitable environment. So.
Thank you.
Yes. Thank you. So I apologize if this is a bad question, but given if an exoplanet is close enough to observe and has an atmosphere, is there much opportunity to observe its atmospheric spectra? And if so, can you tell anything about the surface composition of the planet from the spectra itself?
That's a great question.
Sorry.
Never apologize. It's a really good question. So yes, absolutely. And in fact, I think getting the surface. So the point is, yes, if you basically, so spectra basically are colors, understanding colors. And so yeah, if we could measure the brightness of the planet in different colors, then we could learn something about the surface conditions. And so actually, I was part of an experiment called Epoxy, which was, there was a deep impact mission. There was a mission that was sent out to explore the solar system. After it was done, the camera was left over, and we used the camera to turn back to the Earth and observe the Earth as it turned on its axis, right? Yeah. And we measured the brightness of the Earth in different colors. And then this was work done here at the University of Washington with Nick Cowan and Eric Agol and others. Basically what they did is they took the brightness in different colors. Okay, so you just measure how the Earth, you measure the total brightness of the Earth in a blue wavelength and a green wavelength. And they said, let's pretend I know nothing about the Earth. Can I make a map of the Earth? Can I make, because it's exciting, right? Because the point is, at sometimes the Earth looks bright and sometimes it looks faint because it's reflecting. And they actually concluded that the Earth would have a certain number of continents and a certain number of oceans, and the continents would be green as opposed to brown due to forests. And it was amazing what you could learn just from basically those spectra. So it was really a really nice study.
Yeah.
Proof of concept.
That's really cool. Thank you.
So what would you say is the probability of finding a system elsewhere that has multiple exoplanets, kind of like our solar system here that has like 9 planets or whatever, and how many would have multiple habitable exoplanets?
Yeah, I'd say the great news is we know about such systems. So I was telling you about this system where we know there's 2 planets. There's a really exciting other system around a nearby small star called TRAPPIST-1. You probably may have heard TRAPPIST-1. It's got 7 planets, of which nominally something like 3 are sort of roughly in the habitable zone. And there's other systems as well. Certainly from Kepler, we see other systems, although those are generally too far away to study in detail. So it looks like these small M-dwarf stars are very good at making lots of rocky planets, like a whole standing army of rocky planets, of which a bunch of them can often be in the habitable zone. So you could, in our solar system, there's really only 1 planet in the habitable zone, but it looks like there's other stars where multiple planets would be habitable around the same star.
Hi. So you mentioned that you have systems in place to figure out the diameter and to figure out the so basically you can figure out the density of the planets, also the atmosphere. Once it comes to it, would you be interested in finding out more things about the geology so you can make it more fine-grained to know not only whether it's rocky, but what sorts of things are going on, and kind of, are there kind of any expectations that you have as to what sort of geological conditions would be optimal for life?
Oh, that's a great question. Yeah, so the habitability of a planet, of course, depends on much more than whether it's rocky and whether it's temperate. And I think one of the big questions is whether it has an active geological cycle, right? So the Earth has plate tectonics. It means that the atmosphere and the ocean and the mantle, the rocky mantle, are all talking to each other. They're all exchanging gases. And that's really important for the long-term habitability of the Earth. There's some planets in the solar system where they're no longer geologically active. And we think that that's a big reason why they lost their atmospheres. They don't have a magnetic field that protects the atmosphere. And they don't have a way of, like on Venus, once it didn't have oceans, it had no way of getting all that carbon out of the atmosphere. And so it's like Venus and the Earth have the same amount of CO2. It's just that in Venus, it's all up in the atmosphere. Ours is all down in the rocks because of this process. So I'd love to learn about whether they have active geological cycles, which I would do through magnetic fields. And yeah, in principle, this reflected light idea would tell you about the mineralogy. But in practice, that's going to be a much more difficult measurement. So, yeah.
So let's say this all goes great and you find exactly the planets you're hoping for with the right amounts of oxygen and methane and any other gases. What do you do next to study those planets and confirm that there's life there?
Right. That's a great question. And I would say that I think that so at a basic level, I think there will be the usual scientific dialogue where some of my colleagues will say, I don't believe you. And I'll say, that's fine, but what's your explanation of the data? And they'll have to propose a model. They'll say, I think it's produced by UV light. And I'll say, great, predict something about your idea. And their idea will predict the presence or absence of some other thing that we can measure. So that's how we will proceed. So initially, we'll have some evidence that there might be life. Somebody will come up with a competing hypothesis. What's exciting about astronomy, I hope, is that those ideas can be differentiated through the scientific process. We can observe something else that we will have to design a new experiment for. So that's the big, and I think that discovering life on another planet this way is not a simple, like, make a measurement and we're done. It's a slow coming to an understanding that the only plausible explanation is life, that it'll be a probabilistic statement that will take many years to develop. But then the bigger picture question, the bigger picture idea is, I think going forward, you can imagine all sorts of other really exciting things you'd like to know, like, is it multicellular life? And are there animals? And is it DNA-based? And I don't have a clue how to answer those yet. But I do think that, future scientists will come up with those experiments. I'm not able to, but I think that they will.
I think a lot of our future scientists have already left the lecture tonight. That was an excellent last question. Let's thank David one more time.